So I'm going to talk about from disks to rings. And the workshop is called Computational and Numerical Challenges. So one of the questions might be who is actually challenging us. And I think it's observations, right? Observations don't yet quite line up with our theories. And since I'm only the second speaker, I'm also glad you haven't seen this picture a ton of times today yet, but I'm sure you will see it a bit more. These are the observations that I think are challenging us these days. One thing that they have shown us are, of course, all these rings everywhere. The rings don't seem to line up with snow lines or so. So the idea of snow lines being, at least in the outer disk, being important is almost ruled out. They are also showing us that if these all are planets and they seem like planets or they give some evidence of looking like planets, it's not proof, but a lot of things point in these directions, then it would mean that planets form much earlier than we think they form. We don't have only ALMA, we also have sphere. So here you see the same disk, those two wavelengths, and they look very different. By US food standards, this one would be a hamburger, and this one would be a pancake, if you look at the shape. So you can see that those ellipses kind of are squished together on one side, which is telling you that you're looking into some bowl-shaped flaring disk. Well, these are consistent with being with having the same center. So these are just ellipses with the same center. So one thing that you see immediately is that these particles behave differently. But one thing that is not clear but should be also seen as a bit of a challenge is that the dynamics of large particles and small particles are different. And they are also different from particles of growing particles because these particles change their dynamics as they grow. So that's why we are working on 2D models. This is work that Joanna Trzaskowska is presenting, so I won't talk too much about it, but just to tell you what's in the simulations. It's 2D hydrodynamics plus lots of different particle sizes that are also interacting with coagulation. So you can get a particle size or even a size distribution at every point in the disk. Again, all the details will come in Joanna's talk. There's just one more example that she's not going to talk about that I want to show you. Here we have a vortex in one of the disks. You have probably seen similar simulations before. But now, when we look at the size distribution, it really tells us that something else apart from the dynamics is going on. Because what you see here, the blue line, this is now a cut along azimuth. So you see the vortex almost as like a weak pressure bump in azimuth. And these are now different particle sizes. And I want to draw your attention to the small dust, which you would usually say is just following the gas. And it does so in most parts of the disk. But then in the vortex, something else is going on. So the curve outside of it is consistent with a constant dust-to-gas ratio. But then small particles are actually produced by collisions in the vortex. So in the vortex, it looks almost like you have trapping of small dust particles. And this is because you trap the large particles and the large particles fragment. Okay, now with all these observations from the D-sharp survey, we can start to make statistics about those rings. And there's a couple of important things we realized. One is, for example, that there's good evidence for trapping. So the green line is the radial size of the beam. So you want to make sure that is smaller than the feature you're looking at. And the orange line is the pressure scale height. And the gas shouldn't be narrower than the pressure scale height. So for all these points, being above the green line means they are resolved. Being below the pressure scale height means there has to be trapping. And based on this, you can get some dynamical constraints on this ratio of the turbulence alpha divided by the Stokes number. So of course, quite some uncertainty because we don't yet exactly know what the scale height of the gas is or what the gas density is, but it gives you dynamical constraints. And we can start to put these things together if we now also, for example, consider the particles being only 200 micron in size. There's some evidence from that I'll show you in a moment. But if you now constrain this, then you get some pretty low upper limits for alpha, which is also consistent with some of the recent results. So here's a summary and a kind of back of the envelope estimate. If we believe that alpha is as low as some people are saying, this comes either from line observations or from the fact that the millimeter emission is really narrow, so particles have settled a lot and they are not mixed up efficiently. Second ingredient is this particle size of about 200 micron. You get this from two lines of arguments which are physically related. One is from polarization. This is a bit more constraining. And the other one is a lower limit, that the particles have to be at least 100 micron based on the albedo measurement from D-sharp. And the third ingredient is what I just mentioned, this alpha over Stokes of about 0.1. So if we take this now together and we say alpha, let's say, is for example 10 to the minus 3, that gives us a constraint on the Stokes number. And if we know the particle size, we can calculate what gas surface density we would need to make all of this work. And this is at, for one example I picked, for an outer disk, you need 100 to 200 grams per square centimeter, which is just not impossible because at this point your disk weighs roughly as much as your star. But if you now allow alpha to be quite a bit smaller, then things become more reasonable. So you end up with about 20 grams per square centimeter, and this is about a Q of 2 in the outer disk. And interestingly enough, from other arguments, there was also recent work by Diana Powell, which we'll hear more about, I think, later this week, which finds the same value for the outer disk. So if all of this should work dynamically together, then I think we need to consider lower dust to gas ratios and higher gas densities. But I think the question of how all the small dust remains up in the atmosphere is still an open question. Okay, that brings me to challenge 2. That's where it really gets uncomfortable. And the reason is we're talking about theory, but we need to still have a look at reality. And we want to compare the two from either side. But somewhere in between is this nasty field of laboratory astrophysics that brings us, for example, the collision velocities that Kathy was already mentioning, but also the opacities that help us translate between those. So back to the D-sharp rings, here is an estimate of the peak optical depth of these rings. And this is in itself already quite interesting because we see they are not 0 and they are not much larger than 1. They all somehow line up at around 0.4 or so. So this is a question in itself. Why is it like this? And there's a couple of answers. One might be related to scattering. That is a recent paper by Zhao Zhu. But for those rings, they don't seem to be enormously optically thick. Otherwise, they would start to become flat-topped. So I'll point you to another talk by Sebastian Stammler, where we think that this might be related to planet formation, giving a natural explanation to this limiting optical depth. But now opacities come, of course, in setting this optical depth. And if we, for now, assume that the disk is optically thin, then you can roughly estimate the intensity in this way. You have the Planck function. And then you have basically in the optical thin limit the optical depth, which is opacity times dust surface density. And this is something that has been used for decades. You can measure then the resulting spectral behavior of this. And you know roughly your temperature, so you get a roughly 2 from the Planck function, and the rest, the beta, that tells you something about the optical properties of the dust particles. But this is now where it becomes uncomfortable because already since 2005, there are a couple of laboratory measurements around the literature that show that there's a temperature dependence. And that's not a temperature dependence like you get for Rosland mean opacities, where it just comes from the averaging over the Planck function. This is where really the optical properties of the particles change with temperature. And the change is quite substantial. So if we go from 300K down to even 30 or 10K, you see that there's easily a change of an order of magnitude at long wavelengths. Short wavelengths, interestingly, are not really affected by this. And this opacity now goes directly into your mass estimate. If you go back here, so if you want to get the same intensity that is observed, but your opacity is lower, then your dust surface density needs to be higher. And now if we look at where this applies, you can see this is a typical temperature map of a protoplanetary disk, and everything below the white line is below 30 Kelvin. So most of the disk is so cold. Most of the disk in this case would be below at basically the lowest opacity measurement in this case. And this has more important consequences. One, this is a typical almost HD 163296 like disk setup, but just with one gap. And the blue line is the emission profile that I get for this disk just in itself. This is what the image would look like at D-sharp wavelengths of 1.25 millimeter. But if we now take into account that the opacity is reduced as a function of temperature, then we would get this one. And if there's a gap in it, for example, the disk does not manage to go back up above the sensitivity limit in this case. So if you want to measure disk sizes, your disk would, instead of being like this, suddenly look like this, so much smaller. And this is something, as long as we don't know what the opacities are, something we need to watch out for. Okay, I still have time. So this is just about how we measure the particle sizes briefly. This is from Andrea Isella's paper. What you see here are the velocity, the CO channel maps. And you always get these ear-shaped patterns. So what you actually see here is emission of the front side, like the side that's pointed towards us of the disk. But then there's also this fainter patterns, like here, like this one, and this one. And what's now interesting here is that you see in the front side of the disk is very bright. The back side is a bit fainter because it has to travel through the disk. But then these ellipses are where the dust rings are. And you can notice that the background emission is missing at the point of the dust ring. So here's a bit of a toy model of this. So you get the strong foreground CO emission and the weak background CO emission. So first of all, the background is a bit weaker, but then at the point where you have the dust in the way, where the dust rings are, it is even weaker because it gets extinct by the dust emission. And this is something we can now use because we get the dust emission itself, which depends on the dust absorption opacity. And if we measure the extinction of the CO background compared to its unextincted case, we also get the extinction opacity. And the two together give you the albedo, or what's plotted here, something like 1 minus albedo. So you have 0 albedo if your largest particles are small. And as you increase your particle size, at some point, the albedo drops. And this is now quite interesting in terms of the opacities. Opacities, as I mentioned, is a dirty business, and you can vary them a lot. But this albedo effect is more general. So even if you put in quite exotic opacities, you basically always get this behavior. And then only at longer wavelengths, sometimes things look differently. But this gives you a good measurement of how large your particles should be at least. And you see the gray area is a measurement of D sharp, showing us that we have to have roughly at least 100 micron-sized particles. Okay, the last challenge, I think I'm going a bit faster than I thought. The last challenge is initial conditions. I think we can all agree if we run models, we need to put in some initial conditions. And these are enormously uncertain because oftentimes they are set by our current observations of disks. And then if you put in what you currently see and let the model evolve and it evolves away from there, then sometimes we are surprised that we don't get out what we put in the beginning. So now that we have large samples of disks from various millimeter surveys, we can make use of them and try to be a bit more agnostic about the initial conditions to see what do we actually have to put in to get out what we see today. So here are some very preliminary results. What you see here are is a relation between the millimeter flux of a disk and its effective radius. And all these points in the correlation are from Anjali Tripathi's paper. And overlaid are now a large number of models. So everything you see flickering is a small track of one of these models. And this is now a large grid with pretty arbitrary initial conditions. We are still working on these, so it will probably at some point be more of a Monte Carlo optimization instead of a simple grid. But there's already a couple of interesting things that come out of it. One, for example, and this is not completely equally sampled yet, but you see from those simulations that most of their lifetime live in the right allowed observed range. You see that most of them are starting with a very high dust to gas mass ratio, so somewhere around 10%. So this is yet another indication, I think, that the particles, the disks have to start out heavy, and if alpha is indeed low, then it would also make sense that nowadays we might still have pretty high gas surface densities. Okay, one more last thing, and that is also related to initial conditions. That's now the disk build-up stage. So here, I was motivated by the fact that we see all the substructure in these D-sharp disks, and in some cases we think it's planets. And the question is then, how can you build a planet as quickly, like after a million years or a few million years, so far out already? And there have been some works looking at infalls onto the disk. It builds up the disk. Also, Joanna had a paper about it. And typically, it doesn't help you a lot if you use something like a shoe infall model that gives you mostly a pretty smooth disk to start with. If you instead look at current simulations of star formation, then, and also some of the observations even, then it looks like the infall is not as ordered as the traditional shoe infall. So there might be streams coming in from one preferred direction and from one preferred source of specific angular momentum. And what it means would be that you basically dump a ring of material instead of a disk. And this ring, kind of by definition, should live about one viscous time scale. And if alpha is indeed so low, then this would be a long time. And that would be plenty of time for the particles to grow and to start drifting towards the center of this peak. So that's what I tried out here. On the top, you see the dust size distribution. And there is like a disk to start out with, but a very low mass disk, so it's almost like no disk at all. And then here, I try to have some made up, so this is not really motivated by any theory or by modeling, just a localized infall rate that is constant for a certain amount of time and then just disappears. And on the same plot, you will see a planetesimal formation. So this is based also on Joanna's work and Duke Cronenberg's work, where we, of course, don't simulate streaming instability in this case, but we take the results and make them into a recipe where once you have reached the right particle sizes then and the right dust-to-gas ratio at the midplane, then we convert dust into planetesimals. And so I let it go. You see how the infall is happening here. The particles are growing quite quickly. And let me try it again. And they grow, in this case, significantly before the gas ring is really disappeared. So this is another case of alpha of 10 to the minus 4. And you see in this case, as the peak also moves inward, like we expect from viscous theory, also regions where you form the planetesimals doesn't give you just one delta function, but it gives you a certain range out there. And another way of looking at this is in terms of the total mass budget. So we start here with, as I mentioned, a very low mass disk. Then the infall phase brings the dust and the gas mass up until it stops. And then it stays constant for a certain while because we dumped everything in the outer disk, so we don't lose anything. But then at this point, the dust particles are getting concentrated enough for streaming instability to kick in. And then you quite quickly and quite efficiently form planetesimals there. So you see that in this case, drift is not really a problem. If you sum those up, you almost get back a dust-to-gas ratio of 10 to the minus 2. A bit of dust is lost, of course. but you quite efficiently convert everything into planetesimals in this case. So this is another example of where I think the initial conditions really matter. And of course, the next step would be to follow up what happens with the planetesimals that are born in such a bump. So that brings me already to the summary. I think with the ALMA observations, we now see dust evolution in action. One thing that I only touched upon, but I hope it became clear from some of those parts, are that global properties sensitively depend on microphysics, mainly on things like the fragmentation velocity, as Kathy already mentioned, but also things like the probability of sticking that goes linearly in the lifetime of the disk. And also what we see, given a certain model, also depends on the microphysics. So this is some inconvenient field because we need to rely on the uncertain laboratory astrophysics, but it's something we need to watch out for. And last but not least, if we now have all these detailed observations from ALMA and from SPHERE, they are very detailed, so we should better also build detailed models that capture these physics. Of course, still trying to understand them. So the to-do list here is, and at least in some parts, it's really crucial to have dust dynamics with particle growth. Listen to Joanna's talk later this week. Opacities are enormous source of uncertainty, and I think we don't even have captured the whole range of uncertainties there. And I think one of the biggest challenges we face these days is initial conditions. We have now seen all this structure in class 2 disks, but we don't really know when it started, what causes it, and how it evolves. So I think we have to, at some point, really watch out for disk build-up, class 0, class 1 stage, and to understand what's happening in those cases. Thank you for your attention.
Questions? Jeremy.
Say a little bit more about the temperature dependence of the opacities. What were the structures of these grains? What's the physical mechanism for that temperature dependence? And
okay,
what are the implications for the ISM, where there's a large...
Yeah, and as a matter of fact, people think they do see it in the Planck data as well. They do take temperature dependence into account there. But what it comes down to is really some kind of a solid state origin of this. It has to do with somehow, don't ask me the details because I really don't know, but it has to do with vibration states in the solid state and how much freedom it basically has as you go to smaller temperatures. These vibrations can be suppressed, and then you just don't absorb as efficiently anymore. It was also shown to depend sensitively on the structure of the material, so it seems to mostly apply to amorphous materials. So if you have like a proper lattice, then it doesn't seem to make such a big difference. Yeah, most of the material was some kind of magnesium silicate or so that has been tested for this. There's more data, I think, coming out soon, but it seems, I think, from what I talked to those people, it seems mostly to be the question of amorphous or not amorphous.
I have also a related question. So we have this problem, chicken egg problem with opacity temperature, right? So I have a couple of small questions. Could that be that we don't get the opacities? So you said that we basically overestimate the opacities. What if we underestimate the temperature instead? And the second thing, like how to break this chicken egg problem of opacity versus temperature, because the opacity depends on the temperature, but the temperature depends on the opacity. So where to start to solve this problem? Okay,
yeah, thanks for the question. Actually, it brings me to the point that I wanted to mention but forgot. So first, maybe with respect to the temperature, I think you can, of course, change the temperature, but at some point it's a question of the energy balance. So I don't think that you can globally completely reduce the temperature or increase the temperature of the disk, because in the end you just get the heating from the star, and that's all you can work with. Then with respect to measuring it, I think there's now a couple of interesting new works that have come out in the last months or so, One is by Giovanni Rossotti, who looks at disk sizes and the fact that you see pretty sharp edges as a function of wavelength. And this is something that I think you should only get if your grains are rather compact. If the grains are porous, then you probably would lack the feature and the opacity that you need. And the other one is by Diana Powell, that basically, similar to what I've been showing you, there uses dynamical properties and timescales to say something about how much dust has to be around. And if that amount of dust is roughly in agreement with what we infer from the flux, then it tells you something about the opacities, that they should be order of magnitude correct.
Okay.
Yeah.
Thank you.
Could you explain a bit more how this info promotes planetismal formation? Because I would naively think it dilutes the materials instead of enhance the solid to gas ratio.
Okay, why should it dilute it?
If you keep dumping 1% materials, but you have a local enhancement, then it drives the local concentration down instead up.
No, but the situation here is that we have a certain infall rate on a, in this case, pretty much empty disk, and the infall happens in dust and in gas, right? So you 1% of the mass that's dumped is in dust, and then the concentration really happens dynamically because if you dump a ring will again start to trap particles and concentrate it. The other question that I didn't talk about here is, of course, then the stability of this ring, right? So if you dump that material far out, it might be becoming gravitationally unstable. And that's, of course, a thing we are just about to start working on when you take particle growth and self-gravity into account in 2D.
I want to ask about the grain size. I mean, the scattering results, polarization, self-scattering tend to constrain dust size to be about 100 micron or so. And usually, millimeter observations assume, well, grains already grown to millimeter. And just now you were saying, yes, from albedo, the lower limit is, say, 100 micron, so that they can more or less, you can sort of reconcile that. But that really means the maximum grain size is just, say, 100 micron? If that is true, how would you then form planetesimals, etc.? What's your take on it? I know this is still controversial.
Yeah, and I think I haven't understood it at all yet. So I think there's a couple of things that we were just too used to and are now just learning that they are not actually true. One is, for example, the millimeter spectral index. That was always used as an argument that you have to have at least a centimeter or millimeter sized grains in the disk. Now, and no one thought that disks out there could be optically thick. But now with all the rings, you bring all the material into small regions, and then you might actually get most of your emission from an optically thick region of the disk. So once you have this and you smear it out to the observations we had before, then everything might look like it has to be large grains, but it could as well be just optical depth. Right? Then with regard to planetesimal formation, that's a good question because I think if alpha is so low and the Stokes number cannot be too high, then you have only Stokes particle sizes, particles with Stokes numbers of 10 to the minus 3 or so. And then planetesimal formation might become, of course, a bit more difficult, or it might take longer times to form them.
Like in your planetesimal formation model, the last part of your talk, what's the maximum grain size?
So in this case, it became larger, but I don't think that's a problem because this was supposed to be the disk as it's being built up. While I think what we see now is only million-year-old disks, where I think the structures come not from infall or something, but they are formed maybe by planets that are already sitting there.
Okay, I think we should perhaps move on. So thank you again, Til.